Perfect. Okay, then I start now. I will talking about quantum communication, and one of the big goals of quantum communication is to produce quantum networks. So what are quantum networks? Quantum networks consist out of nodes, and these nodes can process or store quantum information, and they also have a light-matter interface. So using this light-matter interface and using quantum channels, they can send photons to each other, and they can distribute entanglement between the nodes. So in the end, you could think about applications such as distributed or blind quantum computing, or what is important for this talk is you can use these networks for cryptography. This talk will be about the building block of such a quantum network, which is a quantum network link. And the realization that we have is we use single rubidium atoms, which are trapped in an optical dipole trap. And we can generate entanglement between the Zeeman state of the atom and the polarization of a single photon. This we do in two of our traps. We collect the photons, send them to a Bell state measurement setup, and by entanglement swapping, we can generate entanglement between the two atoms. So this is a top view of our experiment. So here you see the LMU campus in Munich. Where you see the locations of our two labs. So we have one lab at the Schellingstrasse, and the other lab where Trap 2 is located is at the Schackstrasse, roughly 400 meters away. The two labs are connected via a 700-meter fiber channel, which we can use for the photons to exchange them between the two labs. So we're not the only ones that do long-distance entanglement distribution. So over the recent years, there were actually quite some interesting and really nice experiments. So for example, and not only using single rubidium atoms, so here they use atomic ensembles to entangle them, or at the Rempe group, they use rubidium atoms, single rubidium atoms coupled to cavities. Or in Delft, they now for the first time realized a three-node network using NV centers in diamond. I will be talking about two recent results in our group, and one is about quantum key distribution. So we already had a nice introduction in the previous talk, and this will be a special or a more advanced way of QKD, which is device-independent QKD. The second part of the talk was actually nicely introduced also by Andreas Reiserer. That is that when you work with rubidium, if you send the photons at 780 nanometers through optical fibers, then you have a lot of losses. So here you see the event rate of our atom-atom entanglement over the fiber length. And if you go to, for example, 10 kilometer of fiber length, then at 780 nanometers, you have no events left or no photons left at the end of the fiber. So we need to come up with frequency conversion techniques, which I will present to you as well. Okay, this is the outline of the talk. So first I will talk to you about some fundamentals of our experiment. So how do we generate the atom-atom entanglement? Then I will talk about the device-independent QKD results. And I will end with the telecom conversion. Okay, how do we trap a single atom? So we have our high vacuum setup in which we create a mod of rubidium atoms. Then we shoot in an optical dipole trap laser, which we focus down narrowly with a microscope objective up to roughly 2 microns. The focus of this trap is exactly at the position of the mod, and then we can load one atom from the mod into the optical dipole trap. The reason that we only get one is because the focus of our dipole trap is so small. Then the nice thing about this setup is that the atom is trapped exactly in the focus of this microscope objective. So the microscope objective also collects the fluorescence from the atom. So we collect the fluorescence, use a dichroic mirror to couple it out, and then we can couple the fluorescence into single-mode fibers. The probability, if the atom sends out a photon, to couple it into the single-mode fiber is in our experiment around 1%. If you then look here at this single photon detector, then you can clearly over time see two levels. So you see a low level when there's no atom in the trap, and a high level when we have an atom trapped. Then the next step is to generate atom-photon entanglement. So for this, we first prepare our atom in the MF0 f=1 state. We shoot in an excitation pulse, and then there are 3 decay channels of the atom. So the atom can go to this, and this state. However, by the orientation of our collection setup, we do not collect photons that are of pi emission, and therefore we generate the following entangled atom photon state. This we do in 2 of our traps. So we generate 2 pairs of atom-photon entanglement, and then we shoot the atom to a Bell state measurement setup. For this to work, for good entanglement swapping, what we need to have is indistinguishable photons. So they need to be indistinguishable spatially. So this we do by using a fiber beam splitter to combine them on. Temporally, they need to be the same, and this we do by synchronizing the 2 excitation pulses to the 2 atoms up to 400 picoseconds, and spectrally, the photons need to be the same, and this we do by 2 times using a rubidium atom and zeroing all the fields during the atom-photon entanglement generation process. So the moment that we get a coincidence detection here at our Bell state measurement, then we know that entanglement generation succeeded. The success probability of this process is around 1 in a million. However, we can repeat the tries quite fast, here at 52 kilohertz. So we expect the rate of this atom-atom entanglement of around 1 success in 6 seconds. Okay, after having this herald, after generating the entanglement between the 2 atoms, we can read out our atomic states. This we do by a state-selective ionization scheme. So by setting the polarization of this readout beam, we can excite a certain qubit state. And this excited state we then directly ionize by at the same time shooting in an ionization beam. So by tuning, so this readout is then completed by OR directly detecting the ionization fragments. So this is a picture of our setup, and you see channel electron multipliers. So what we can do is we put 5 kilovolt voltage over here, and then we can directly detect the ion or and the electron, or we can just use fluorescence detection and check, is the atom still in the trap, yes or no, and that gives our final result. So then we come to the next part, and this is about the implementation of device-independent QKD with this setup. Let's first take a step back. We go to QKD. Actually, the previous talk was gave a quite good of an introduction. So why we want to have QKD. And QKD systems currently are commercially available. So this is just a figure from Toshiba having 2 quantum units which are in different cities and are connected via a 10-kilometer optical fiber. And users can use this system to distribute keys. However, for QKD to be secure, there are always some assumptions that you need to make. So the first one is that quantum theory needs to be correct, but there are more assumptions. For example, that the users need to have freedom and secrecy of the measurement settings, and also the outcomes of the measurements need to be secure. So if this was the only one, then if these were the only assumptions, then it would have not actually been a big problem. However, for normal QKD, there are more assumptions. So for example, in the security proof, you assume things about, you make assumptions about the states, for example, that you use, or you make assumptions about the inner workings of the devices. And therefore, the users actually need to check their devices if they really behave as specified in this proof. So the users need to have trust in the devices. Another thing is to make the people that make the devices can make some mistakes, or they can not see some security breaches. For example, it has been shown that the detector dark times can open up implementation flaws, or can open up possibilities to eavesdrop a key. So you need to really, the good thing here is that it's always really easy to come up with a solution for these problems, but you never know if you're protected against all those implementation vulnerabilities. So then in the 1990s, there was actually an idea to overcome all these issues, and that was device-independent quantum key distribution. And this gives a relaxation of the assumptions that you need to make about the devices. So for example, you don't make any assumptions on how the devices work themselves. How can it then still be secure? So if the 2 devices share an entangled state, then you can observe non-local correlations by violating a Bell inequality. And by only looking at the input and output of the devices, you can evaluate this Bell inequality, and you can do 2 things. So you can secure, or you can make sure that the devices behave properly and secure. And the other thing is that you can directly bound or upper bound the maximum information an eavesdropper can have about the key. So how do we implement this experimentally? So for this, we need to have entanglement distribution between two remote locations. However, we need to do this with really high fidelity. We need to have high detection efficiency of our state to close the detection loophole, and we need to do this with a high rate. These ideas came up in the 1990s, and then end of last year, within 1 week, there were like the first 3 proof of concept implementations of this. So besides our experiment, there was also an experiment done at the University of Oxford, where they use entanglement of strontium ions. And there was another implementation in Fe, where they used entangled photon pairs to verify that you could implement the IQKD with this setup. So then about our setup. So what was the protocol that we implemented? So for normal for the original DIQKD, what you do is you generate an entangled state, and the 2 users, Alice and Bob, measure this state. So Alice has 3 different settings, and Bob has 2 different settings to measure the state, of which setting 2 and 3 for Alice, and 0 and 1 for Bob, are chosen such that they maximize the violation of a Bell inequality. And they're also used to evaluate this Bell inequality. So then there's one more pair of states, so Alice 0 and Bob 0, and these measurements are chosen to have maximally correlated or anti-correlated outcomes, and the measurement outcomes here can then be used to generate the key. So for this, we actually worked together with René Schwanneck and Charles Lim from the National University of Singapore, and they added an extra setting, or they improved a bit on this protocol. And by adding an extra setting, they could make the protocol more robust against noise. So how does this work? So in the normal case, when you have 3 settings, then you always assume a worst case, and the worst case is that Eve knows which setting you use for the key generation. However, if you now randomly choose between 2 settings, then Eve doesn't have this, and these settings are orthogonal to each other, then Eve doesn't have this information advantage anymore. So in 50% of the 50% of the times, Eve will not measure in the correct basis and will not gain maximal information. So therefore, it's harder for Eve to get information, and therefore, this scheme can handle a bit more noise. Okay, then what do we see here? So here we see the S value, so the CHSH S value, and the quantum bit error rate. So this is how many mistakes you actually made when you expect perfectly correlated outcomes. And in the color-coded, you see the asymptotic key rate. So for higher fidelity entangled state, your S value goes up, your Q-bar goes down, and you come here at the highest at the point where you have the highest asymptotic key rate. So if you compare this to the original protocol, the 0 key rate boundary is at a bit higher fidelity. So this is actually the gain of adding this extra setting. So then, where were we? So 5 years ago, we did the loophole-free Bell test, and there we showed an S value, which was where we actually were really happy with, of S equals 2.2. However, if you now look for the DIQKD applications, then this is not enough. So this is roughly a fidelity of 80%, and this is not enough to do anything with DIQKD, so we had to improve our entangled state. So we made several improvements here, and I actually want to highlight one. So in our entanglement generation process, there's a high probability that the atom decays back to the F equals 1, MF equals 0 state. So this happens with a probability of 1/3. And since the excitation pulse that we shoot in is roughly 20 nanoseconds, and the lifetime of the atomic state is comparable, around 26 nanoseconds, it can happen that this decay occurs when the excitation pulse is still on. If this happens, there's a possibility of a second excitation and a second decay. If we now look at the atom-photon state that we get out here, it's perfect. Right? This is exactly the state that we wanted to have. The photon that we can detect is entangled with the atomic state. However, the temporal shape here is different. And for our 2-photon interference, the temporal shape of our photons is also important. So while having the correct atom-photon state, we still get a reduced atom-atom state fidelity. So what you see here is the a simulation of this process where you see the detection time of the photons. And you see here this bump, and this is this second excitation, which happens in 4% of the cases roughly, which reduces the atom-atom state. So what we did is we somehow took a brute force approach here, and what we said, it's a bit counterintuitive, but we said we do not accept photons that are emitted in the beginning. So we set an acceptance window, and by setting this acceptance window, we could increase the interference contrast from 88% to almost 99%, and this increased the fidelity of the obtained atom-atom state from 80% to 90%. So if you now look here, so by changing the start of the acceptance window, so moving the start value here, you see that the number of events we get goes down. However, we increase the fidelity of the obtained atom-atom state. Another improvement that we made is we implemented new microscope objectives for 2 atoms, and thereby we could collect more efficiently the fluorescence of our atoms, and we increased the event rate by a factor of 6, and therefore we could somehow make this trade-off of getting the higher fidelity. Okay, then what was our setup? Alice is in lab 1, Bob is in lab 2. They both have a device. Alice's device is a single atom trap together with the Bell state measurement setup. Bob's device is a single atom trap, a beam splitter, and a single photon detector here. Both devices can get an input. This input sets the polarization of the readout pulse, and they give an output. And the output is the number of fluorescence counts. If it's above or below a certain threshold, then this gives a binary output. Then we start entanglement generation tries. If we get a successful coincidence, we send a signal back to Alice and Bob and say that the state is ready to be measured. Then we implemented 2 quantum random number generators, and at Alice's side, 2 random bits are generated to select 1 out of 4 inputs, and at Bob's side, 1 random bit is generated to select 1 out of 2. And then for this to work, it's important that the in and outputs of the devices do not leak to the. And also the in and outputs, of course, are stored in the local storage. Then for this to work, it's important that the in and outputs of the devices do not leak to the environment. For this, we had to implement a spectral filter and a shutter at Bob's side. So the readout here is nicely aligned such that it leaves the laboratory, and this we cannot have because then the measurement setting or the input to the device would go to the environment. So therefore, we implemented a spectral filter here to filter this out. And also the fluorescence detection, after a readout event, there's 780 light also nicely leaving the laboratory. So therefore, we closed the shutter before starting with the fluorescence readout. At Bob's side, or at Alice's side, this was not necessary because the photons do not leave the device actually, because the BSM is included in the device. So then we let our experiment run for 75 hours. We get more than 3,000 entanglement generation events. And then here you see the data that we got. So on the horizontally, you see the 4 settings from Alice, and the 2 different plots are the settings from Bob. Then in blue, you see correlated outcomes of the 2 devices. And in red, you see the anti-correlated outcomes of the devices. We fit the data, and then we get visibilities around 87, 88%, with which we can estimate our fidelity of 89%. Then we use the green settings here to evaluate the S value, and the yellow settings to evaluate the Q. So these were the results that we got. So by improving the fidelity, we now see that we're nicely in the asymptotic positive key rate regime. So the S value we measured was 2.6 with a QBER of lower than 8%. And then we can generate 0.07 entanglement or secret bits per entanglement generation event. Normally you would do a finite key analysis to really say, okay, now we have really distributed the finite key. However, for that we need to have a lot more events. So we would need to let our experiment run for a few months even. So therefore we did a statistical analysis. How certain are we that we're in the positive key rate regime? And this we can say or claim with 99%. Okay, then I come to the second result, and that was about quantum frequency conversion to increase the range of our quantum network link. So for this, we teamed up with Matthias Bock and Christoph Becker from the University of Saarland. And what they did for us is they developed really efficient and really nice quantum frequency conversion devices. So what do we use here? We use a PPLN waveguide, and in the PPLN waveguide, we have different frequency generation. So we have for 780 nanometer photons coming from the rubidium atoms. We mix them with this bump field at 1607 nanometers, and then we convert our photons to 1517 nanometer. So the process of this conversion is actually polarization dependent. And this is a problem because we have our state is encoded in the polarization of a photon. So what we did is putting the PPLN waveguide in this Signac interferometer by placing here also a PBS and a half-wave plate. And now what we get, so we split our two arms, let's say horizontal vertically polarized light, but then we rotate one of the two arms such that in the PPLN waveguide we have two counter-propagating beams, however with the same polarization. So both of them can be converted with an efficiency up to 96%, and then we rotate one of the two back, combine them on a PBS, and after filtering out the single photons, we now have a device that is polarization preserving, which also has an external device efficiency, so this already includes the filtering of around 57%, mainly limited by fiber couplings. For this, we need to spectrofilter with 27 megahertz, and we get signal-to-noise ratios of more than 100. So this is a pretty good device, and also it was stable over weeks. Okay, then the original idea was to move one of our nodes to the MPQ and really have entanglement distribution between the LMU and MPQ, but it turned out to be hard to get a fiber between those two institutes. So what we did is we put node 1 into our first lab and node 2 into our second lab, so they're still 400 meters apart. However, we put in now these two quantum frequency conversion devices, and then we could plug in we could plug in long fibers on spools up to 33 kilometers. And then what we do is we convert the photons, we shoot them to the middle station, and now the middle station does a Bell state measurement in the telecom to swap the entanglement to the atoms. And then what we also do is the moment that we get our two photon coincidence, we send the heralding signal back to the nodes, and we implemented an extra delay here to really simulate as if the two nodes were separated by the 6, 11, 23, or 33 kilometer. Then again, we need to do the entanglement swapping, so we need to have good two-photon interference. And now you can think, okay, if you converted the frequency of the photons, does this still work? So what we do here is we use the pump light for the two QFC devices originates from the same laser source. And by originating from the same laser source, we pump with exactly the same frequency. And therefore, we are also certain that after conversion, the two photons still have the same frequency in the telecom. Here you see the photon shape, and you see that we can nicely overlap our two photons. And we get here an interference contrast of around 95%. Here we still have some of these two photon events where I talked about before, so this reduces the number. And we have a tiny bit of noise from the converters that also reduces this number a bit. So this is not yet corrected for noise. Okay, then the results. So here you see over distance, so this is the fiber length. You see the fidelity that we obtained. So we first did characterization measurements for the atom-photon entanglement distribution for the two nodes. And then you see that they don't start at the fidelity of 1 because there are some errors in the entanglement generation process or in the readout. And they decay over time, and this is because we have atomic decoherence. Then we did the atom-atom entanglement measurements, and you see what we expect here to get is somehow the multiplication of those two visibilities times the interference contrast, and this is exactly what we observed. And to somehow verify or characterize that this drop in fidelity really comes from the atomic state decoherence, we did another set of measurements where we did not plug in these long fibers, but we only delayed the atomic state according to the distance that the photons should have traveled. And then we see a similar decay. And yeah, this is actually a nice day to present these results because this afternoon they should come online or they will be published. All right, so what are the next steps that we're working on now? So one of the things that we want to do is we want to get rid of this decay. So we want to get rid of the atomic decoherence. We want to make this line straight. So for this, we actually implemented some tools recently that were developed in the Rempe group. So initially, our atomic qubit is encoded in these two MF states of the f equals 1 level. However, if a magnetic field comes by, then these magnetic states decohere. So what we could do is we can transfer our population here to the f equals 2 level. And those two states, if magnetic fields come by, they behave a lot more similar when a magnetic they behave more similar to magnetic fields. So therefore, we could actually reduce the sensitivity to magnetic fields by more than a factor 500. So this we implemented recently. So what you see here is in red, we see the visibility of our atom-photon state over the readout delay. And then in red, you see our initial basis. So that is the basis where we see more magnetic field noise. And then after transferring the atom or one of the qubit states to the other MF state or other F level, you see that we increased the coherence time of our atomic state up to 5 milliseconds. So what we could do by combining and the frequency conversion and this new encoding of our atomic state, we could also measure atom-photon entanglement after the photon propagated over up to 101 kilometer fiber. All right, let me summarize. So I talked about our quantum network link in downtown Munich, and I told you how we entangle our two atoms. I showed you recent results of one of the first proof of concept experiments of DI QKD, and I showed you that we can now entangle two atoms when the photons travel through up to 33 kilometer fiber. And with that, I want to thank you for listening.
Okay, thanks for the very nice talk. We have time for questions. There's one already.
Hi, so thanks again for this very nice talk. I actually have two questions, and I hope they're appropriate in this setting. First of all, with the whole quantum cryptography aspect, is there any good reason to believe that nobody will come up with just a mathematical algorithm that's both quantum and classically secure? Because I think once you have this, there's no reason to invest billions in quantum cryptography if you're already secure. And question number two would be, does this type of protocol actually protect against man-in-the-middle attacks as you would expect them today? So instead of Eve listening in on a key exchange, just convince you they're Bob. So you do your key exchange with Eve, think you exchange a key with Bob, it works, great. They do the same with Bob. You think you have a secure communication, but you actually don't. Like, this is how you would do it today. Is there any protection against this type of attack as well in this scheme? Thanks.
Let's first go to the first question. I think also in the previous talk there was something about this, right? So there are post-crypto or post-quantum crypto algorithms that actually work quite well. And I think what we're looking for, and also go along with the previous speaker, is that you can come up with some hybrid solution here. So you need to keep in mind that you really play a different game. So you're not securing your information by encrypting it super well, but you really can detect if someone else is eavesdropping you. So I think this is a really vulnerable or really important aspect as well. Then I hope that somehow answers your question a bit. So the future should tell us how this will go. Then about the other attack. So for device-independent quantum key distribution, I think this is secure against the scenario that you sketched, because Alice and Bob really work with a device, and if they really that device needs to be in a secure location. So what you also always assume for the IQKD is that the locations that Alice and Bob have are secure, and you really start doing a bell test between those two locations that are secure. And with only the in and outputs of the device, you can violate the bell inequality and you can secure your information. So I think there's no way so we need to assume those secure locations, and we need to make sure that the device is really in there, and then device-independent QKD should be secure against this scenario. But to have these secure locations, it's not so easy, right? So there is a challenge.
Good. Further questions? There's one question.
Hey, first of all, thanks. This was a really nice talk. And I have a question on the part where you talked about the atom-photon entanglement. Mm-hmm. So you showed that there are these two decay paths with orthogonal polarization. And my question would be, is this splitting ratio naturally 50-50, such that you automatically get a maximally entangled state? Or do you have to, or actually can, control this in some way?
Good question. So here we're lucky with rubidium. So it's really those three levels that we see here. It's really 1/3, 1/3, 1/3 probability that they decay there. Yeah, so we really come up with a maximally entangled state, or we generate a maximally entangled state. Yeah.
Great, then let's thank the speaker again.